In addition to reacting with oxygen nucleophiles, epoxides can also react with carbon nucleophiles. Now, one carbon nucleophile that we've talked about extensively is that of a deprotonated alkyne. And we make these, of course, these deprotonated alkynes by treating a terminal acetylene with NaNH2 to give us our sodium species. This, of course, is a good nucleophile, and it's also a strong base. Now, what's different when you use this versus the oxygen nucleophiles is the steps actually require there to be two steps. First, you react the epoxide with the acetylide, and then you add H3O+. This H3O+ step, it's basically a generic acid workup step. It's basically there to convert lingering RO minuses into ROHs. So, the mechanism of this reaction is pretty much the same mechanism as you saw with the base, with the good nucleophile strong base reacting with an epoxide. The attack goes on the least hindered side, which in this case is the rightmost carbon. And then this product waits around until you add the H3O+ to it. Once you add the H3O+ to it, basically protonate the oxygen. Steps are pretty much irreversible, each of them. And since we're starting with a chiral optically active epoxide, and nowhere does a molecule become achiral, the product is also optically active. Now, one thing to keep in mind is that the terminal acetylides are very strong bases. So unlike oxygen nucleophiles, they are always added on the less hindered side. And you cannot get them to add to the more substituted side by simply adding acid. Mainly because you add a little bit of catalytic amount of H2SO4 in with your sodium species. What happens is you don't get a substitution reaction. Instead, you only get an acid-base reaction. This is your strong base, reacts really quickly with a strong acid, and as a result you get your acetylene, and you this is no longer a nucleophile. As a result, you cannot have it attack that. So, when you're dealing with acetylenes, terminal acetylenes as nucleophiles, the protonated acetylides, they only attack from the less hindered side. Another warning is the alpha carbon that's attacked is indeed inverted. Now if we were to assign R and S to this particular one, oxygen's 1, carbon's 2, it's carbon's 3, and as a result, that type of rotation from 1 to 2 to 3, this stereocenter is S. Now, if we figure out what this stereocenter is, well, this is 1, this is 2, this is 3, rotated around, this stereocenter is also S. We went from S to S. Even though we're going from S to S, an inversion has still taken place. Look at this following example. If instead of adding the acetylide, instead we add, say, sodium methoxide and methanol to it, minus adds, that cracks open the ring, see, same stereochemistry as up above. Just finish the mechanism by protonating that oxygen. You don't need the extra H3O plus step here because you can have your nucleophile and proton source can coexist with one another. Now if we were to figure out R and S on this, again, 1, 2, 3, that's S, same as above. 1, 2, 3. This one is R. This one, it's easy to see the inversion has taken place because you've gone from S to R. But up above, it doesn't look like the inversion's taken place because you've gone from S to S. The difference is R and S are just labels based off of priority. In this case, your leaving group has the highest priority. And then in your product, your nucleophile has the highest priority. But in the case up above, your leaving group has the highest priority, but your nucleophile, turns out, doesn't have the highest priority. The priority actually goes the other way, where it's this carbon here, which had second priority in the starting material, now has first priority. You can compare that with the bottom case. This carbon, second priority here, second priority here. The only difference is your nucleophile just coincidentally doesn't end up with the highest priority. And as a result, when you just use R and S to designate it, you get an S, even though an inversion has taken place. if you want to make sure that you draw the product correctly, you have to think about the molecule, and you have to inappropriately assign RNS, meaning your nucleophile 1, 2, 3. Your nucleophile gets 1 regardless what its actual priority is, and then you use the same priorities as your starting material. So in this example right here, this carbon has second priority, this carbon has second priority, this carbon here has third priority, this methyl has third priority. Your leaving group had first priority, your nucleophile should have first priority then. Your leaving group and your nucleophile should have the same priority in order to double check. So when you do this, this is S, this is R. It's a double check that you have done, that you have indeed have done the inversion. Okay, now this stereocenter is only to be used for double checking your product. This is not actually an R stereocenter, it's actually an S.